All right, AP Physics. It's time for Unit 2 of AP Physics 2. We are getting into thermodynamics. This is a pretty deep topic, so we'll talk through all the major concepts. There'll be a couple things that we'll cover in class outside of some of the stuff mentioned here as well, so we will expand upon a lot of it, but we want to make sure we get you the basics here, okay? So first, running through the big ideas, most of them covered here in thermodynamics because we are talking about energy, and we'll expand upon these as we keep going here, okay? First thing I want to make sure we mention, energy and particles. Okay, matter is always in motion, and that's an important thing to realize. Even solid state matter has vibrating particles within it, has electrons orbiting nuclei, and so forth and so on. So everything is always moving, and so there's always going to be energy in particles. Particles of gas, liquids, and solids, they all move, as I just mentioned, and this really goes into what's known as kinetic theory. And kinetic theory refers to the different setup of molecules based on the general temperature is what it comes down to. Now we say temperature and we measure it via temperature. We'll get into this in just a sec here, but really it comes down to the amount of heat or thermal energy associated with that. So let's hit the difference there. Heat is energy produced or transferred from one body to another. There is a transfer of energy happening here that will go along with our conservation of energy and everything else that we've covered so far with energy. And so we've actually got movement of energy when we talk about heat. Temperature is the measure of that. So a good way to kind of look back and forth at this is time is always moving forward, right? We would use something like seconds or minutes or hours to measure time. Temperature measures heat. All right, they are not the same thing. Temperature is a measurement that we put on the amount of heat or thermal energy that is existent within a system. Okay? So because all particles are moving, this is a measure of the kinetic energy and or the thermal energy of particles. And that's really important too. Kinetic and thermal energy are essentially the same thing. And this is why when you take your hands and you rub them together, they get warm because you're changing directly your kinetic energy of the movement of your hands into the thermal energy that happens because of the friction between your hands. So to look at different temperature scales real quick, we've got Fahrenheit, Celsius, Kelvin. You've seen all these to some degree. Our standard is going to be Celsius here, but I do like to mention that, that Kelvin is present also. And so make sure that we're kind of working with both of these. We won't really use Fahrenheit at all, but you'll see both Celsius and Kelvin. So I say Celsius is the main, but we'll end up using both. So in fairness, prepare to see and utilize both of these and know that the difference between Celsius and Kelvin is 273, with Celsius always being the higher number. You've learned this in a lot of different spots, so I'm not going to elaborate too much on that. Conducting heat. So adding thermal energy increases the amount of kinetic energy that atoms have and changes the state of matter. When objects can conduct heat and hold more thermal energy, they will change state. And that's really what we're looking at here, right? And this is why we've got our state of matter down there in the bottom left, and the movement of thermal energy through them based on the same material, the same molecular makeup, just changing state of matter here based on how much thermal energy it's got. So conductors are more likely to accept this thermal energy, and we see some of the conductors right there, right on the right in the bottom right. Aluminum, really metals is what it comes down to, nails, keys, nickels, things like that. And then insulators are less likely to conduct thermal energy, so things like rubber and plastic, and you see there also cloth or Q-tips, clothespins, rubber bands, all of these are going to be insulators, not likely to conduct thermal energy. A vacuum is a little bit different case than everything else that we've talked about so far because there is no conduction happening in a vacuum space. A vacuum refers to an area where there is empty space. So even in the air around you right now, the reason you might feel hot or cold, even though cold doesn't really exist, is because your body temperature in comparison to the thermal energy, in comparison to the thermal energy in the air around you is different. And so less thermal energy in the air around you makes the air around you seem colder. It's still warm because there's still thermal energy there, but it will seem colder in comparison to everything else that you're feeling. Now, when there's a vacuum or empty space, so think like out past our atmosphere in space, or a container that we pull all of the air out of, then it's going to be a perfect insulator because there's no medium through which for this thermal energy to transfer. Okay, so we use vacuum insulators for things like thermoses or whenever we want to keep hot or cold in a specific spot. Instead of putting in insulating material, we can just remove all material and have a vacuum state. Now, the movement of energy here can happen in three different ways, and this is a quick review basically of some chemistry, and you're going to see a lot of chemistry concepts in this unit as a whole, so let's realize that. We're a short review here of chemistry for some of these items too. Three main methods that we're going to consider for thermal energy transfer. The first being conduction. All right, this is transfer because of collisions between particles and matter. We have to have a structure to the matter that allows for that energy transfer to happen fairly easily. So you're typically going to have solids here, and those solid materials then are going to, the energy as it transfers into and through the solid will cause vibration in the particles of the set state of the solid and allow that thermal energy to move through it. So you see a person here holding a metal object with one end in a flame. Eventually, if it is a conductor, the hand there is going to get hot and potentially burn because that conduction will happen through that object and the heat will transfer through it. Now, when we're looking at fluids, we're more likely to have convection. All right, so convection is transfer here in a gas or a liquid, so any type of fluid. As the warmer and cooler objects, they really circulate and spread thermal energy through that process. So cooler objects, when it comes to fluids, become more dense and more tightly packed. As they become more dense and more tightly packed, they fall downwards, and the less tightly packed or warmer parts of this fluid will be pushed up above the cooler parts that sink downwards. So you've heard the saying a lot, hot air rises. That's not actually true. Colder air actually falls and thus pushes the warmer air up. So the same end result is happening, but the mechanism is different, and that's, I think, something important to realize. So that's convection. Our last one here is radiation. This is the transfer of energy through electromagnetic waves. And so there doesn't necessarily need to be particles there for this to happen. This is one of those spots where you could have a heat transfer through a vacuum. And this is how the Earth gets heat from the sun. It gets radiation from the sun. And so we get that energy transfer happening through waves as they move through empty space and then bombard the planet once they get here. Other sources for this are things like a fire. So you see this happening right here. And what's really interesting is in this one picture, we have all three types of thermal energy transfer. You see the radiation coming out from the fire that's heating this whole process. The convection is the fluid in the fire there. It's going to be moving around. And again, the cooler fluid getting more dense and sinking, where the warmer gets spread out, less dense, and rises. And then you've got a metal pot, so you've got conduction happening through that also. And that conduction is important as the radiation hits it and hits the bottom of it and thus heats everything up. But it's also going to be trouble for this person's hand because eventually it's going to get hot enough that they're not going to be able to hold it. All right, it's time to talk temperature and the internal energy associated with it. So a reminder, temperature is the measure of the average kinetic energy. Okay, temperature is a measure of the thermal energy. Average kinetic energy and thermal energy are going to be the same thing. The internal energy is the measure of the total energy with the system that's included in the system. So far, we've looked at mainly mechanical energy, but now that we look at internal, we are expanding that kinetic and gravitational potential and potentially elastic potential also, to include also now thermal energy. And that's what we mean when we say thermal energy. Heat is a form of energy specific to a difference in temperature that happens as part of the internal energy of an object. So you could have a hot or a cold object rolling along a table. Both will have different levels of thermal energy because of the temperature associated with them. But if they're rolling at the same velocity and have the same mass, then they might have the same kinetic energy. Both of those would be included to determine the total internal energy of those two different systems. All right. This is what happens when you do notes during class changes. So linear and volume expansion. As energy moves through solids and liquids, the volume of them will change. Okay, so most solids are going to increase in length. Most. There's a couple that will actually decrease in length, but most will increase in length as temperature is increased for them. So as they're heated through conduction, you're going to see them get longer, wider, in all dimensions they should move outwards. They'll lengthen at different rates based on the molecular structure and setup of the different particles within them. But in general, we're going to use here this delta L here to calculate the expansion of solids as they are heated, with delta L being the change in the length, and then obviously L naught being the initial length, delta T being the change in the temperature, and alpha being a coefficient that refers to the material there specifically. And so that will vary based on the material. Solids, liquids, and gases will do the same thing, typically increase. And so you see instead of a delta L, so a change in length for specifically a solid, you'll see a delta V, the overall volume change, again, based on the initial volume, the change in temperature overall, and thus the change in thermal energy, what thermal energy is being added or subtracted from that system. And that will be also based on beta there, which is going to be our volumetric descriptor for the material that you're looking at. And we see, right, some of the objects here, we can look, I'll either share that table with y'all or make sure that we can find that. You'll always have those values given. They will be specific to the material and thus something that you need to have or to solve for with the rest of the material given to you. Quick review here of different gas laws. Boyle's law says that pressure and volume are inversely related. Charles' law says that volume and temperature are directly related. Gay-Lussac, I don't know, maybe if I messed that up, I apologize, but pressure and temperature are directly related. And really, in the end, then we have our ideal gas law. These are all things that should have been learned in chemistry, but I just want to make sure that we remember that these are here because we're going to have changes of these values associated with thermal energy moving to and from these systems based on what you just saw there, right? That change in volumetric space. And so we're going to have to consider all of these, or at least partially some of these, as we look at how thermal energy moves and alters systems. So a quick reminder there of how those work, and we'll use more of those as we keep going. A different way to look at this ideal gas law, and I think this is important, right? We've got, instead of PV equals nRT, we've got nKT there, where N is that the number of molecules, right? So the number of moles times Avogadro's number, and K is Boltzmann's constant, something a little bit different. But they're both on your equation sheet. And again, this is going to be something we'll see more in practice, just in case I'm mentioning it now, so that if you say PV equals nKT, we don't freak out and think that it should be nRT. There is a slight difference there, but the function and use of it will be, based on what materials we know, but done similarly to what you've seen before for that ideal gas law. All right, time to actually get into the energy and as the energy moves through these systems. And this is the really, what I would say, interesting part, but certainly the heart of this unit as a whole. A lot of what we've covered so far has been review. So first, law of conservation of energy. Energy is not created or destroyed. Okay, you're going to see Q, and you see that up at the top here. Heat lost is a negative Q, and heat absorbed is going to be a positive Q. So we're going to have Q represent the thermal energy as it moves into or out of a system. And a lot of that's going to be dependent, just like any other type of energy change within a system, on other things happening to or on or being acted upon by the system as this happens. So when one substance is converted into another, there's a conversion of one of these energy types, right? Heat, light, electrical, chemical. Some energy is typically changing also from one type to another. And you've got the example there at the bottom. Chemical energy stored in gasoline goes through a combustion reaction, aka it burns, and thus is converted into mechanical energy through the engine as a whole, and we see that happening over here, right? So we've got chemical energy stored in the gasoline. We've got an ignition process that then burns it, and it causes an expansion of the volume there as it burns, and thus pushes the piston down, and does so repeatedly, and the pistons move back and forth over and over and spin a drive shaft, and your engine works. So we've really got chemical storage and then combustion and thermal energy happening here within a mechanical engine, and that's essentially how most mechanical engines work, is by utilizing these principles. So again, heat being Q here is a transfer of the thermal energy between two objects of different temperatures in contact. So that's our basic definition, and something I want to hit fairly specifically here. So I'm going to say it one more time. Heat, thermal energy, Q. Heat is a transfer of thermal energy between two objects of different temperatures that are in contact. Energy is going to flow from objects with higher energy to objects with lower energy. Meaning, in terms of thermal energy, hotter objects are going to transfer thermal energy through heat to cooler objects. Hotter objects here, H, are going to transfer heat or transfer thermal energy through this process of heating to lower energy, and we see that starting to happen here until they're at the same temperature, known as an equilibrium state. So thermal energy comes from heat, and then temperature is that average kinetic energy as we've talked about already, and it's the quantitative measurement of hot or cold. And again, it's not really cold, it's more hot or less hot. Cold really would be absolute zero, and that's it, and that's pretty much all that's going on. But since we use common descriptors here of hot and cold, I'm going to mention those in here as well. The units. We know units to be joules for energy, and you see that that's still on here. You can fairly commonly see calories for thermal energy as well, so the amount of energy required to raise 1 gram of water by 1 degree Celsius. That can be important because it's a more specific measurement or a specific unit involved in heating when we're talking about transfer of thermal energy. So while still quantifiable in terms of joules because it is energy, calories are something that we will see here some also. Okay. All right, now for the fun words. Enthalpy. Enthalpy is referring to internal energy of a system. We might see E, and that's kind of your common note for total energy overall, but really we're going to see U here often, capital U, as being the enthalpy or the total energy within a system here. So total of all possible kinds of energy present, both kinetic and potential. Energy is transferred into a system based on this and result in a change in the system based on how these flows happen overall. So when the system either absorbs heat, so if we went back to our cooler object example and it got thermal energy from the warmer object, it would be increasing in enthalpy because it would be absorbing heat, and this we're transferring energy into the system, or when the surroundings do work on it. So if something around it were to do work on that, that puts energy into that system also, as we've talked about. We know that doing work on a system adds energy to the system, right? We've already known that for sure. Now, energy is transferred out of a system, either, and I'm going to go to that second one first right here, right? When the system does work on the surroundings, meaning the work is going out and thus joules are leaving the system, or when the system releases heat. So if it has 1,000 joules of heat and it's put next to an object with 500 joules of heat, 250 are going to move from one to the other to level them both out at 750, and so we would have energy transfer or enthalpy moving out of the system also. And you kind of see the options here, Q in or Q out, and work it on or work into the system, work being done on the system, or work going out of the system based on that system doing some work somewhere on the surroundings. So work, something clearly that we're going to see a lot of here. It's the common type. A common type is associated with chemical processes, okay? And so if you've taken or are taking AP chemistry, you've seen this to some degree too, but compression and expansion of gases can create work. And that basically happens because as a volume increases within a system or within an object, it's going to cause a force to be pushed outwards as that volume increases, and thus a force will be applied, some object will move some distance, and we have work being done here in these cases. So work in delta V must have opposite signs to look at this, and I think that's really important. Work going into or out of the system is something we want to make sure we note here. So we see W equals negative P delta V. What that means is the work equals the pressure times the change in volume, and that's going to be in the opposite direction of the change in volume. Okay? So if a volume, a delta V, if it expands, okay, if it's moving outwards, right, then that means that something had to happen to cause that expansion, and then the work is going to be negative there. If we have delta V as negative, if it's getting smaller, then we've got a negative there overall for delta V. We're going to end up with a positive work being done. That means something's applying joules via work to a system to cause it to move downwards there. So we have a negative V that's negative, a delta V, that's negative, and thus we have the negative delta V here multiplied by the negative that's inherently in this equation, and we end up with a positive work, meaning work was being done to cause that lowering of volume. Okay? And we'll see a lot of this, and we'll talk about how this all works in a little more detail in class. Now that we're talking about enthalpy, and enthalpy is really is the first law of thermodynamics, we want to make sure we make this connection here. So the first law of thermodynamics is that the internal energy of a system changes through heat flow into or out of the system, or when work is done on or by the system. Essentially what we've just stated the last couple slides here, okay? So this means energy can neither be created nor destroyed. And in short, that's all there is to it. It's thermodynamics' version of conservation of energy here, is the first law of thermodynamics. So energy of the universe is constant. There is no change in energy anywhere ever. It's just changing from a type A to type B and moving through systems and flowing around here. So you see positive Q plus Q is heat flow in, and negative Q being heat flow out. Plus W is work done on a system. Negative W would be work done by the system on something else outside of it. So our positive and negative there are just direction. And if I probably said that in your head to yourself if you have taken my class. Entropy. Now this, because we've mentioned enthalpy, I feel like it's something we want to make sure to mention. But in short, entropy is physics for chaos. It's really what it comes down to. It's the degree of disorganization in a system. So entropy is the physics word for chaos. All right? An increase in disorder represents the opposite function of work. And if we look at this, I think it's easier actually to look at the more disordered on the right and realize that we would have to do work to make it highly ordered, right? We have to apply force to move those objects some distance to get to this highly ordered state. What this is saying is entropy is the opposite of that. More entropy means more heat and thus the spreading of these objects and more chaos. So as you take an object that's structured, let's say that's flammable or explosive, we add thermal energy to it, we increase the entropy as it expands and increases in energy and increases in temperature and explodes or burns or whatever else it might be. That's what it means to have and to increase entropy. All right. So entropy being the structure here of different systems, whereas that enthalpy is the measure of the energy inside of them, and they are both very clearly related. A little more specifically, we got to get through all of our laws of thermodynamics. So I'm going to be pretty quick here. Energy in equals energy out. And so we have to have conservation of energy. And again, that's all that this is really saying. We've got a dry hairdryer right there. We use electrical energy, and it generates thermal energy and heat, kinetic energy and the movement of the air, and sound energy, which is going to be the vibration of objects and then that transfer of energy into your ear so that you hear it. And it's still a type of energy as well. We can see here that we have a heat transfer and work being done from state 1 to state 2, and thus an internal energy that could change based on that additional addition being done here, right? And I think just adding these NASA slides when they're available here gives you another way to look at this. And we see, right, so between any two equilibrium states, the change in internal energy is equal to the difference of the heat transfer into the system and the work done by the system, okay? We see those things happening to some degree here, and thus we could have a change in internal energy. Now, what's important is defining those systems as well. So in an open system, and we've talked about these in class for sure too, but an open system, heat can flow in and out easily, right? Classroom with the door and window open, got an open system, we can have thermal energy flow without much of a problem. But in a closed system, a fully closed system, no heat can escape on its own without some sort of work being done. So this would be more like a classroom with the door and window shut. I do realize that there is some space still where that could move, where thermal energy could move in and out, but for the most part, we'd be looking at an easily open system versus an easily closed system, and I think that's just a good way to help you remember it. Our second law of thermodynamics says that heat flows from warmer objects to cooler objects. We've mentioned this earlier too, but want to make sure to define it as the second law of thermodynamics. So thermal energy, heat, transfer from hotter to colder spaces. So heat cannot flow from cooler to a warmer object unless we push it that way. Okay? So we can't take a lower temperature and cause it to continue to go lower if it's surrounded by a higher temperature unless we do work on it. And this is what like a fridge does, is it does that type of work to remove the thermal energy from inside of the system. Okay, so we must do work in that case, and this is why you got to plug a fridge in instead of it just staying there and becoming colder somehow. All right, and so we've got this delta Q, this transfer here of entropy based on that heat transfer by temperature from hot to cold. So there exists a useful thermodynamic variable called that entropy there, and that's going to be represented by S. A natural process that starts in one equilibrium state and ends in another will go in the direction that causes the entropy of the system plus the environment to increase for an irreversible process and to remain constant for a reversible process. So we're going to see them for reversible processes go back and forth here and be equally, and that's what we're going to handle more here in physics. But the irreversible that it's referring to, heat can be lost and thus not transferred back if you have something like a chemical reaction, okay? In which case, you can't necessarily move back from two products once a chemical reaction has happened, and so some of that heat can be not lost, but removed from the system as a whole during a process like that. So heating objects. There's a number of ways that you can heat an object, right? We could push the object, which means we could do work on the system. I'm pushing my hand past my other hand, and I'm doing that repeatedly, and thus I'm heating my hands in between here by pushing and doing work on the system and changing that kinetic energy into thermal energy. I can remove or add mass of a different temperature. You see this all the time. You want a colder drink? What do you put in it? Something with lower thermal energy, typically ice, right? So removing or adding mass of a different temperature. And then finally there, we can transfer energy from high to a low temperature through some heating method. Those heating methods being our conduction, our convection, and our radiation. All right. So this is how we have these changes in thermal energy and thus movement of heat through a system. Now we got to talk about how work can be done by gases as that heat transfer causes a change in the, I won't say the properties, but the values of properties of gases. So as they expand or compress, work is being done either by the gas or on the gas. And another good way to think about this is that combustion engine, where you've got a little particle of gasoline that's ignited, and thus we have that expansion and that change from liquid to, well, really a different state also, but expansion in volume there is what's helping cause these pistons to move. That's kind of the idea we're doing here, right? We got work done by a gas, whether it's combusting or on its own or something like that. So work on a gas, work being done on a gas that's in a closed container. Some external force is applied to the gas, resulting in a change in pressure and or volume. So you see this here on the left. If we apply some pressure or some force or something to this to cause this system to move downwards and be less, we're doing work on that gas. When we stop applying that force and stop doing that work, then we're going to have an expansion where this surface is going to move back upwards, and now this gas is doing work by pushing the lid up and adding work or pushing work out of the system. If there were to be something on top of this or something like that, it would apply the force outwards to the surrounding area. The amount of work being done then is shown by the pressure and volume change of the gas, and we see that right here. In the case of this, now this has to be what's referred to as an ideal gas, right? So it can't be overly compressed on its own, which is to say I can't push the gas together and have it just change state. It has to stay as a gas, okay? But that's going to be that negative PV that we looked at earlier. And so we see PV there being the change in volume, and I mentioned we'd come back to this more, right? But so the direction of the work, positive or negative, is dependent on what the work is being applied to. So it's not going to be just positive x-axis is, or plus, and negative x-axis is minus, and so forth and so on. It's more the direction of this flow of joules overall. When the gas does work, the volume of the gas increases. We get a delta V that's big, and thus we have positive work. When the work is done on the gas, the volume of the gas decreases, and thus work is negative. Now, I'm saying this for the second time purposefully because having expanded upon a couple other things in between, I'm hoping at this point it's like, oh, okay, that makes more sense now that I'm seeing that again, and we'll see it in practice more too. So because of this positional characteristic, pressure is negative when considered work done by a gas. And we've seen these before. All right, so thermal energy transfer overall. And we're going to get into some of our diagrams here soon and see how some of those work, okay? But as previously discussed, thermal energy transfer happens in numerous ways through materials. We talked about that. Measuring this transfer of energy will depend on the amount of heat present and the physical properties of the material. That is important. We've got to remember that there can potentially be different measurements of conductivity and thus different ways that we need to gather the thermal energy that's present also. So increasing thermal energy transfer will mean a greater delta T. If we're transferring more thermal energy, we'd have a greater change in temperature, a greater total change in heat. It would take less time to do that if we had a greater thermal energy change, which is to say, if I put ice into a room temperature drink or ice into a heated drink like a coffee or a hot tea, the time that it takes for that thermodynamic equilibrium to be hit will be different based on how much energy, thermal energy, was present there. A greater A, so a greater area, will cause for a more rapid transfer of heat. So we see the area for heat to transfer on. It can be more efficient and quicker given a greater area and less length. So if you needed to heat a solid object, a shorter object will heat faster and a thinner object also will heat faster than a longer or thicker object. And different materials are going to have different values within this as well. So properties of materials are to some degree a portion of this too. Some of our thermal energy transfer equations. So the rate of energy transfer in watts. This is essentially the power of transferring thermal energy. And thus you see the P here. A couple different ways to measure that. Q, which is just joules, right? Energy transfer in joules divided by time in seconds. And then that second one there leads us to the same final value as far as units go, and we'll end up doing a unit analysis on that almost certainly, right? But it's a different way to measure that, and thus you see that altered around there for the thermal conductivity K, that this and this are the same equations. This has just been solved for K, okay? So thermal energy transfer equations. A couple of the constants that come along with this, conductivity. So conductivity of materials, it's based on the thermal conductivity, and that's, again, the structure of the molecules in these different materials. Conductors typically have a higher value for this, and thus will have greater heat transfer, and insulators will have a lower value. So you see some of these numbers over here. We should be using diamonds a lot more, it looks like, to transfer thermal energy, because it does so better than silver and copper and brass and all these other conductors. And then you see down towards the bottom there some very low values, meaning those would be insulators and not allow for heat transfer. Things like wood or air or styrofoam. And a reminder that a vacuum would essentially be zero if it was a true vacuum here. Now, as these properties change and as we change energy and move energy through a system, we're going to want to look at how the properties of that system change, because we can see, and we've already talked about how work is done on or by systems based on a change in pressure and a change in volume and those types of things. So we now need to talk about PV diagrams. And this is going to be the way that pressure, volume, and temperature are related when we describe a system. They're going to move through these processes and be represented on these diagrams by these processes and by these arrows. And it's going to show the change in pressure and volume, and then determine what way work is being done and how heat is going into or coming out of a system. Okay? So pressure, volume, temperature, all related. Thus, reading the diagram here showing pressure and volume can help us determine changes in temperature. All right, so what direction things are moving in and how these lines are moving and how they're shaped is going to help us determine that. The area under the curve for these graphs is equal to the work that must be done to change from one state to another. So in the case here, it actually would be the shaded area in the middle. Over here would be the work done under there. What that means is that pressure and volume, as previously related in terms of work, right? Work being negative P times delta V. Thus, we can determine how much work is done via the area under the curve of pressure and volume. That's essentially what this is saying. That's what you see there in that second diagram right over here where it's showing the work being the area under there. There are some specific systems that we need to look at and understand the names for and why they are the way they are here. And then we'll get some more practice with this later on in the class as well. So isothermal systems. Iso being one, so constant, staying the same, thermal being temperature. So if we have an isothermal system, what that means is everything along those lines, everything along that red line is at 500 Kelvin. And so if the pressure goes down, then the volume goes up. And that's all this is saying. And at 400 Kelvin, it would follow this black line. And at 300 Kelvin, it would follow this blue line. So all this is saying is, given the same temperature and the temperature being constant, we see the relationship then between pressure and volume. Okay? And we are essentially right there looking at this top and or potentially bottom curve and seeing how those change in these systems. Okay? An isovolumetric system is basically saying, again, iso, one, and volumetric staying the same then. So it's saying that there's one volume. And here we've got our sides of this overall system, okay? We're going to have no area under the curve here, obviously, because there's no curve to find the area under. What this is saying then is, as the volume is constant, if the pressure goes up or down, we are then going to have, as you see right here, heat either being added or extracted from the system, okay? So if the volume is constant and the pressure is changing, that happens because heat is moving into or out of the system. Isobaric, similar, but the pressure staying constant this time instead of the volume. So isobaric meaning constant pressure. Okay, it's not going to be isopressuric or something like that. Baric, bar, coming from the word for heavy, typically refers to high pressure. You've heard of this term used potentially in like meteorology and things like that as well. And so what we've got then is a spot where we have a constant pressure and a change in volume. And you've probably guessed it also, going back to what we looked at before. That means work is being done by the system or on the system, depending on the direction that we're looking at here. Okay? And then finally, we've got an adiabatic system. This is kind of its own. So far we've looked at isothermal, constant temperature. Isovolumetric, constant volume. Isobaric, constant pressure. Adiabatic is a little different. There's going to be no heat exchange here, okay? The pressure and the volume will change, but no heat is actually going into or out of the system here. So we have energy transfer only as work being done in this case. Heat stays the same, only work changing here. So AKA work is done through mechanical means rather than heat transfer. This is a complex Greek origin, right? It basically says not go through. And so the shape is similar to the isothermal systems, but always will have a lower curve. And we see this lower curve here in adiabatic systems, and that's because heat is not transferring. So if we had similar systems compared to each other, I think it's worth just trying to remember the names here, looking at these here, isobaric, isochoric, isochoric also being what we saw for isovolumetric, okay? We're also going to see this as isochoric, so please realize that both of those terms could be used here. So isobaric, isochoric, isothermal, and then that adiabatic that we looked at. This is going to be different types of systems based on the gases that are there. That's going to be the major determining factor of the different curves and the different lines that are present, and we'll do some work with learning how to read these. We'll get back to our big ideas overall, and hopefully this is helpful in getting us through all the material for thermo and getting you started. See you in class.